Math Olympiad problem all the way back in 1999. The Bay Area Math Olympiad is middle school and high school level math. But just to be clear on what we mean by proper divisor, let's take 10 for example. Every integer has 1 as a divisor. Okay, but 2 is also a divisor of 10 that is less than 10, and so is 5. So essentially you just omit, technically 10 is a divisor of itself, but we leave that out. So these are the only proper divisors of 10, namely 1, 2, and 5. Okay, so we're trying to prove that among 20 consecutive integers, there's going to be an integer in there that's less than the sum of its proper divisors. Okay, now 10 is greater than the sum of its proper divisors. And only notice that this sum, if you take the sum here, the sum is 8. Sum's equal to 8. And that sum is less than 10. But we're looking for a number that's the other way around, okay, where the sum is actually greater than the integer itself. Okay. Now, the big observation here is if you have 20 consecutive integers, one of them is guaranteed to be a multiple of 20. And that just follows from the division algorithm. One way of looking at it, assume the first integer is a multiple of 20, then you're done. Otherwise, the first integer would be in the form 20k plus I, where I is an integer. And eventually that I is going to be equal to 20 since there's 20 consecutive integers. Therefore, you would have exactly one number that's a multiple of 20. Okay. Now, so we're going to call that one. We'll just call it 20k. All right. Now, the proper divisors of 20k, and I left out. Well, it's you can just see them here. We have k, 2k, 4k, 5k, and 10k. Okay, well notice that these sum up. The sum of this would be what? 3k, 7k, 12k, 22k. So the sum here is 22k. The sum equals to 22k. And that meets the condition because 20k, of course, is less than 22k. And again, k can be any integer. So that completes the proof of this. Now, in the competition back in 1999, okay, so we can write QED here if you want. Even if you don't want to, I'm going to write it. But right here, the problem they used in 1999 was 12 consecutive. 12 consecutive. So the only two numbers I'm aware of with this property are 12 and 20 at this point. And I look for, patterns like, 12 consecutive, abbreviated. Notice that 12 is equal to 2 squared times 3. So it's a prime squared times another prime. 20 is also a prime squared times another prime. But I tried it with some other numbers in this pattern and they didn't work. So I don't see any discernible pattern where it works. These are just 12 and 20 are the only two that I know right now. But anyway, that is all. Did we prove it, folks? Yeah, I proved that it's less than the sum of its proper divisors. We did just that. Okay. Thanks for viewing.